Okay guys, we're going to have a look at the second mechanism on the AS syllabus, which is called electrophilic addition, and it's electrophilic addition to a carbon-carbon double bond that we're looking at. So the first thing I suppose we need to look at is the goings on in a carbon-carbon double bond, which we've looked at in class already, and we should know between two carbons we have four electrons, two pairs, and they form what we call our sigma bond and our pi bond. We should also know that those pi bonded electrons are held less strongly by the nuclei of the carbons than those in the sigma bond. The pi bond electrons, remember those sideways overlap of our p orbitals, which are just that little bit further away from the nucleus than our sigma electrons. Okay, we also need to remember that this is an area of dense negative charge. You have a lot of electrons, I know it's only 4, but you have a lot of electrons packed into a very small volume of space, so that attracts these electrophiles really very nicely, and because electrophiles are things which are positive or delta positive and can accept a pair of electrons or take a pair of electrons out of a bond. Okay, so we have two things going in the favour of the carbon-carbon double bond for it to react. We have first of all the fact that there's the pi bonded electrons, which are held a little bit less weakly than the sigma bonded electrons that you would have in an alkane, and you have this area of dense negative charge in here. So let's have a look at what actually happens. So this is your first introduction and mechanisms to what we call curly arrows, which are arrows which show movement of a pair of electrons, and they show movement from where the electrons begin, obviously in the pi bond here, to where those electrons are attracted or go towards. So let's have a look. My hydrogen bromide here arrives, because bromine is much more electronegative than hydrogen, it arrives as a polar molecule with a delta positive and delta negative end. Other molecules might get a dipole induced on them as they approach this area of negativity, but this one arrives with a delta positive charge on it. Okay, now that attracts the electrons, specifically the pi bonded electrons, towards it. Now hydrogen can only accommodate, as you know, 2 electrons in its valence shell, so the electrons that are already there get pushed away, and we show that both the electrons by again another curly arrow moving from where the electrons begin to where the electrons are being attracted towards, which is to the bromine now. That now causes this bond to break, but unlike our last mechanism where it broke in what we called homolytic bond fission, this time it breaks unevenly, or in other words heterolytically. So in other words, this hydrogen gets neither of the 2 electrons, and the bromine, as I've shown down here, has got both the electrons. Okay, this shows the first attractions that go on, and then if we move to here, this now shows the hydrogen from the hydrogen bromide has formed a bond with the carbon. This carbon here has had to give one of its electrons in order to form this bond, because the hydrogen has arrived with, as you can see, no electrons at all, which means that we have now got this rather strange looking positive carbon atom here. That is called a carbo for carbon, cation for positive ion. So we've got this, I'll just move that charge closer to the carbon, okay, which will attract, of course, our negative bromide, which has been made here. Note that originally the bromine was delta negative, now it's fully negative, so be careful in an exam. And make sure that you show the arrows going from where the lone pair begins to where again it's being attracted towards. Okay, this is a very quick part of the reaction here, because our positive and negatives attract very quickly, as you would imagine, and the bond forms very quick, and we get our final product. Okay, now in this particular instance the product doesn't matter whether I put this hydrogen onto that carbon or the hydrogen onto this carbon that I've put it on. I get the same product. Ordinarily though, you need to be able to predict which carbon it will go onto, and remember that's Markovnikov's rule, and it would always go on to the carbon which has got the most number of hydrogens already on it. Okay, and you can read about that, Markovnikov's rule, and I'll maybe do a video on that at a later stage. Okay, So hopefully that clears up electrophilic addition mechanisms. You need to be able to obviously adapt this mechanism for whatever compound the examiner happens to give you, but just remember the reaction always happens around the carbon-carbon double bond. So you just find the carbon-carbon double bond in the compound, and then you just draw whatever is on the groups A, B, C and D as separately. Okay, so hopefully that helps, guys, and any queries or questions I will sort them out in a while.